Hello, this is a content checkpoint video guide for the first exam on the Balanced Force particle model units. To start off with here, we have a list of things that you need to know going into this exam. Make sure that you look over this list. Make sure that you understand everything on it, because I think a lot of times people ignore these big blocks of text because they don't want to read them, but this is literally the things that you need to know going into this exam. So take some time, make sure you're comfortable with all of these things. Going down here to section A and practicing these skills, the first one here is making free body diagrams and system schemas. So it says here, we're going to start off, we read the situation. I think the next good step is to figure out whether it's balanced or unbalanced, make the system schema, make the FBD, and that's sort of the order that I'm going to go in. This says a cat falls with increasing speed. The system is the cat. So if it's increasing speed, you should think that's not a constant velocity. So the forces on this one are going to be unbalanced. So we start off there. Then we've got this cat. That's our object of interest, is the cat. It's interacting with a few things here. One of the things is the Earth. That interaction is gravitational. One other thing that it's interacting with is the air. Now, you might choose to leave this off. I think it makes sense to include it though, so I'm going to put it on there. If the cat wasn't falling too fast, it would have pretty negligible air resistance, but that's kind of up to you. Alrighty, so going over here now, making the FBD. Something important on this one to realize is that there's gravity pointing downward, Fg on the cat by the Earth. Alright, and there's the air resistance force pointing upward. But the air resistance force needs to be significantly smaller than the gravitational force because it's going to be changing speeds as it goes down, so not a constant velocity. So a little tiny arrow there, much larger arrow for the gravitational force. This next one, we've got a girl pushing a box across the carpet. The box is the object of interest. Of course, the girl is going to be interacting. If you're pushing a box, it's a normal force. Something else here, the Earth, of course, gravitationally is interacting. This is going to be pretty much every one of them is going to have Earth included. All right, then additionally, the carpet is going to have a normal force there because the two surfaces are pushing against each other, and that's what makes a normal force occur. All right, and you might think that those are your only three forces. However, it's constant velocity, which means that the forces need to be balanced. Let's go ahead and start like we would. Let's pretend we had not realized that this other force is on there that we're going to end up adding in just a second and say, all right, here are the forces we've got. We've got gravity downward, Fg on the box by the Earth. All right. Then we've got going upward, Fn on the box by the carpet. All right, and then the other one, the girl's pushing it, so Fn on the box by the girl. All right. Now, the other thing, okay, so we look at this and you can see visually it's not balanced, right? So that should clue you in, like there needs to be another force here, and then you got to think about what it is. We've got a box rubbing across carpet. That probably indicates that there's going to be a friction force in here. All right, and so we get friction there. So there would be friction over here to the right, Fr on the box by the carpet. All right, and these two need to be balanced, and these two need to be balanced, and that's how that one ends up. And we knew it was balanced because it was constant velocity. Next one, an apple sitting on a table. This one's actually like the most basic one that we usually get. It's kind of like the first one we do, so hopefully this one's not too bad for you. We've got the apple. Okay, and then it's sitting on a table, so the table will be an object there. That interaction is a normal force because it's got two surfaces in contact. All right, and then there's going to be the Earth as well. That is a gravitational force. And that's all we got actually on this one. So it's sitting on the table, it's not moving. That means it's got zero velocity, which is actually a special case of constant velocity, which means that the forces are balanced. All right, and so we have these two forces. We've got gravity pointing downward, Fg on the apple by the earth. All right, and then we've got one going upwards. This is Fn on the apple by the table. All right, and those are the same because it's a balanced force. This next one, it says a ball is submerged underwater and it accelerates as it moves straight upward toward the surface. So this one says it's accelerating. Accelerating means its velocity is changing. That means that the forces are unbalanced on this one, so something to think about. We've got a ball. That's our object of interest. Then we've got the Earth. That's a gravitational interaction. And then we have the water. This one doesn't come up all that often, but this is a buoyant interaction. So here's something interesting to consider here. Lots of people come up to me on this question and they say, Mr. Connor, doesn't the gravity go away because you're underwater, because it's floating? Isn't the gravity force gone here? No, that's incorrect. Gravity is based on the attraction between two objects based on mass. If the Earth hasn't lost any mass and the ball hasn't lost any mass, that gravitational force is still there. The only way that we change the gravitational forces is by significantly changing the distance between the objects or changing their masses, and neither of those things has happened here. So gravitational force still exists, and it's still powerful here. The only thing is the buoyant force exists as well, and the buoyant force ends up being more powerful than the gravitational force, so it's going upward. So on this one, we've got FB, buoyant force on the ball by the water. Then going down, and it's going to be a much smaller value, we've got Fg on the ball by the Earth. All right, make those drastically different sizes so that I can see which one's smaller and which one's larger. This next one's a bit of a thinker as well. We've got a magnet that's hanging on the fridge. The system that we're going to be looking at here is the magnet. So, of course, one of the objects is the magnet. We've got the fridge there. We've got the Earth. Gravitational interaction between the Earth and the magnet. The fridge and the magnet, well, you might guess that there is a magnetic force there, so M. All right. The two surfaces are pushing against each other. As the magnet is pulled into the fridge, those two surfaces are in contact, so there's a normal force here. All right. Lots of times, these are all the forces that people get, so I'm going to go ahead and I'm going to construct this as if these were the only forces that were involved. However, if there is a magnet and it's on a refrigerator, it's staying in place, that's at rest, it's zero velocity, it's constant velocity, it's going to be balanced here. All right, so the forces need to balance, so we have to think about these things. Forces acting on this. We've got Fg on the magnet by the Earth going down. All right, then you had this magnetic force. The magnetic force is pulling the magnet toward the fridge. All right, so that is to the left. F magnetic, Fm on the magnet by the fridge. All right, then we've got that normal force that's pushing, the two surfaces are pushing off of each other, but the fridge, if it's in contact with the magnet, the normal force from that is pushing the magnet this way, so we've got Fn on the magnet by the fridge. All right, and then here's the tricky part, right? And then you look at this and you say, wait a second, there's not a third force here going up, or a fourth force going up, so what balances it out? Well, you have to think about what would happen if there wasn't something keeping this magnet up. It would just slide down the front of the fridge, and then you have to ask yourself, what prevents it from sliding down the front of the fridge? Well, usually the thing that would prevent sliding is friction. So there's a friction force on this fridge, between the fridge and the magnet really, that's keeping it from sliding down, and so that's going upwards. So we've got a friction force on the magnet by the fridge here as well. All right, these two forces up and down are equal. The two side forces are equal. Next one here, we've got a ball. It says it's traveling in a parabolic arc after being thrown into the air. A parabolic arc just says it's like it's traveling in a parabola as it's pictured below. And so this one here, you have to think about what objects are directly interacting with the ball when it's in the air. I've said ignore air resistance, so we know there's no air resistance involved. We've got the ball. We've got the earth. That is a gravitational interaction. All right. So lots of people sit here and they think about this at this point, and they're wondering, what other force is here? Like, what is this force keeping the ball going forward? Well, you can keep thinking, but there are no other forces here. You don't actually need something to keep the ball going forward because it's already going forward, all right? You would need something to prevent it from continuing to go forward, but if it's already traveling forward in the horizontal direction, it's just going to keep going that way, all right? So the only force acting on this ball is a force that's pulling it down. It continues to travel horizontally because it was already traveling horizontally after it was thrown, but there's nothing else interacting with it. So the only force acting on this ball is the gravitational force. Just one force here, force gravity on the ball by the earth. And this is an unbalanced force. You can tell it's unbalanced because this ball clearly isn't traveling with a constant velocity. If it were traveling in a constant velocity, it would need to be traveling in a constant direction because speed and direction are the two components of velocity, and this is not traveling in a constant direction. It's changing its direction, so it's an unbalanced force in this case. All right, in this section, we're going to be identifying different types of forces that apply. This first section here, we've got a mass. It's hanging from a string, all right, or a rope. So gravity's pretty much always going to be the case unless it's in outer space, so that's kind of a gimme. No friction here, no air resistance. Normal force is when you have two objects, two surfaces pressing against each other. There are no two surfaces in this one, so no normal force. There is a tension force, though, because we have a rope, and the rope is taut. There's no magnetic force because there's no magnet. For B, we've got a gravitational force again. There's objects of mass. They're going to be pulled down towards the earth. Friction, it says it's a frictionless ramp, so there's no friction. Air resistance. Air resistance only applies when an object is moving with a relatively high speed, and it has to have a relatively high surface area. Everything's at rest here, so no air resistance. Normal force. There are two surfaces in contact here. We have the surface of the bottom of the square and the surface of the ramp. All right, so the box and the ramp are pushing off of each other with their surfaces, so there's a normal force there. There's a rope that's taut, so there's a tension force. There are no magnets, so there's no magnetic force. These two, there is a gravitational force because there's objects of mass, and we're going to assume it's on Earth. There's no friction because nothing is rubbing against each other or wanting to rub against each other. Even if these were frictionless, because it's a flat level surface, nothing would fall off here. So there's no friction in any way on this one. Nothing's moving. There's no air resistance. Normal force, we do have two surfaces pushing off each other, so there is a normal force there. But that's it. No tensional force because there's no taut ropes or rope-like objects. There's no magnets, so there's no magnetic force. This one, a box is pulled by a rope and slowly dragged across the carpet at constant velocity. So this is similar to some ones we've seen. Boxes across carpets should let you know that there's some friction involved. Gravitational force on this one. There is no there is a gravitational force. There's always a gravitational force. Friction. I did say as you're dragging a box across a carpet, they'll be rubbing against each other. There's friction. And that is also required for the forces to be balanced. There has to be a friction here. Normal force, we do have surfaces pushing off of each other. The carpet is pushing off of the box. There's a tension force because there is a rope or rope-like object. It says it's being pulled by a rope. So all of those are there. There's no magnets, so there's no magnetic force. All right, going on to the back here, we're starting on some of these problems. Hopefully, these shouldn't be too hard. We've had a bunch of practice. We had a quiz on this, so we'll just go through it pretty quick. So it says two objects have a kinetic coefficient of friction of 1.15. If the friction force between the objects is 30 newtons, what is the normal force that exists between them? So in this one, it's a friction problem, so you'll be given the equations, but just to write it out here, the equation that we're going to be using is FFR equals mu, the friction coefficient, times the normal force. All right, well, we have the friction force. All right, the friction force is 300 newtons. Equals, and then the mu, in this case, is 1.15, and the unknown is the normal force. And so if you solve that for n, you get n equals 261 newtons. And that's all there is to this one. Just write out the equation, plug in the numbers, solve for what's unknown. For problem number 2, it says a spring has a constant of 10,000 newtons per meter. How far would the spring have to be stretched to exert a force of 500 newtons? So on this one, we've got 500 newtons is the force, the spring force. The equation, by the way, that we're using here, actually, I'll write that out quick first, is FSP equals the kx, the spring constant, times the distance that it's stretched. All right, so in this case, the spring force is 500. The spring constant we're given is 10,000. All right, and then x is the distance stretched. That's what we don't know. So if you solve that, you end up getting x is equal to like 0.05 meters, all right, which is good. Or you could say x equals 5 centimeters. Of course, you don't have to say that last one. I just think it's better to give it in centimeters a little bit in the end because it's a little bit more normal to say 5 centimeters than to say 0.05 meters, but it's up to you. Either one of those would be acceptable. Okay, this one, it says 2 charged objects. That lets you know that you're talking about an electrical force. All right, it's separated by a distance of 15 centimeters if they have charges of negative 150 microcoulombs and 70 microcoulombs, respectively. What is the electrical force between them? Is it attractive or repulsive? All right, so we have to plug things into the electrical force equation. That's Fe, which equals K times Q1, which is the charges. The K is the electrical constant, and that's always 9 times 10 to the 9th. So Q1, Q2, the 2 charges, over the distance separated squared. All right. So in this case, that's equal to 9 times 10 to the 9th, which I just put in my calculator as 9E9, times Q1. All right, these are in microcoulombs, so you have to multiply them by 10 to the negative 6th. So 150 microcoulombs is 150 times 10 to the negative 6 coulombs. All right, and then we take that and we multiply it by 70 times 10 to the negative 6th. All right, those are our 2 charges. Don't include the negative in this. We'll use that to determine if it's attractive or repulsive, but just plug in positive values for this because it will give us the magnitude of the force. And it's 15 centimeters, all right? That needs to be in meters, all right? We can't plug it in centimeters, so it's 0.15, all right, meters. 15 centimeters, 0.15 meters, and you have to square that. All right, and then you should calculate that and get 4,200 newtons. All right, and this force here, because it's a positive and a negative, opposites attract, likes repel. This is a positive and a negative, they're opposites, so it's an attractive force. Alrighty. This next one, we've got a situation here. There's a magnet, it's pulling an iron block, there's a spring involved, and so I'm mixing some of these things together. I want you to make a quantitative FBD with the actual numbers on it, all right, to find all the forces acting on it. So the first thing here, you got to identify what forces we've got going on here. We're going to have a gravitational force, and it says acting on the block, so the block is the one that we're looking at. So that's FG because it's gravitational. FG on the block by the Earth. For the next one, we've got a normal force, F normal on the block by the surface. It doesn't say exactly what the surface is, so I'm just going to say S, all right, by the surface. All right, then there's a spring that's pulling the block this way, that's FSP on the block by the spring. So I'm going to put SP there so it's spring to make sure it's not confused with surface. All right, and then going the other way, we have a magnetic force, F, magnetic, on the block by the magnet. All right, figuring out what these are. Gravitational, it's a 5 kilogram block. So you take the 5 kilograms, you multiply by 10, you get 50 newtons for the gravitational force. For the normal force, because those are equal, it's going to equal 50 newtons on the top as well. To figure out the spring force, we need to plug it into the equation, actually. So we've got FSP equals KX, which equals, in this case, the spring constant is 30 and it's 20 centimeters. So it's 30 newtons per meter times 0.20. All right, so we have to convert that to meters. You multiply those by each other, you should get 6 newtons. All right, which means the spring force equals 6 newtons. All right, and then these two forces are equal to each other because it's balanced. So that means the magnetic force is also equal to 6 newtons. So I've constructed an FBD there. It has all the forces. This next one, it says a 50 kilogram buoy is attached to the bottom of a boat, which is sitting in salt water. The density of the salt water is 1050 kilograms per meter cubed. The buoy has a volume of 1 meter cubed. If the buoy is completely submerged, find the magnitude of the normal force between the buoy and the bottom of the boat. All right, so we're going to look here at this buoy. Kind of an interesting setup here, but there are some different forces acting on the buoy. Firstly, we've got gravity, which is pushing it down, F, G, on the buoy by the Earth. Then we've got the buoyant force pushing it up, F, B, on the buoy by the water. And then the last thing here, we've got this normal force that exists between the buoy and the bottom of the boat. You have to think, normal force, lots of times everybody thinks it goes up, but it doesn't go up. It's perpendicular to whatever surface you're in. And if it's in contact with the bottom of the boat is going to be pushing the buoy down. So this is what we're going to have here, a normal force pushing that buoy down. And these are the 3 forces that are acting here. The gravitational force, you can find easily. It's 50 kilograms, so it's going to be 500 newtons. Then we have to figure out what the buoyant force is. The way you do buoyant force is equal to gravity times the density, which is that rho, times the volume of the fluid that's in there. All right, in this case, that equals 10 times 1050, and the volume in this case is just 1. All right, if you multiply that together, you get 10,500 newtons. All right, that means the buoyant force here is equal to 10,500. And then if you balance these out, then that means that the normal force would have to equal 10,000 newtons. And so the answer is 10,000 newtons. Okay, this last page here is just some stuff on Newton's third law. It's kind of silly, this first part, but it's just kind of thinking about what Newton's third law means. And so this first one, it says, draw the direction of the reaction force and state its magnitude, then fill out the missing force statement. So here we've got a gun that pushes a bullet forward with 150 newtons of force. The reaction there is going to be going the opposite direction. It's going to be 150 newtons as well. All right, so I've drawn that reaction arrow in there. And then I would say the bullet pushes the gun backward with 150 newtons of force. All right, for this next one, we've got a girl. She's being pulled down with 330 newtons of force. So the reaction to this, the Newton's third law pair, is that if the Earth is pulling the girl down with 330 newtons of force, then the girl is going to be pulling the Earth up with 330 newtons of force. And then this last problem here, it's a Newton's third law problem. So this is like the interacting objects problems that we were doing that have multiple objects of interest. Try and keep that in mind in this section of the test that's going to be on Newton's third law, that you're probably going to have two objects which are interacting, and you're going to be interested in both of the objects. You're going to be making two FBDs and using that to figure things out. So on this one, what we've got is we've got some different objects of interest. We've got the woman. All right. Additionally, you have the parachute. Okay. We have the Earth, because they'll both be interacting gravitationally with the Earth. All right. And then the parachute and the woman. If you think about a parachute and a person are connected by strings or ropes of some kind, so that is a tension force that exists between them. And then I've said, assuming that the woman's not experiencing direct air resistance, okay, so I'm going to say there's no air resistance on the woman, but there is, of course, air resistance on the parachute. All right, so we've got air here, air resistance. And these are the different forces at play here. I will go through then and make my different FBDs. So for the woman's a pretty simple case. We've got gravity pulling her down, Fg on the woman by the Earth. All right, and you've got tension pulling her up, Ft on the woman by the parachute. Then we think, okay, what do we know here? Well, the woman's a 65 kilogram woman. That means that she experiences a 650 Newton force from gravity. All right, these need to be balanced. So that means that the tension force that she experiences is also 650 newtons. All right, then we go to the other object, which is the parachute in this case. Parachute has three forces you can see from the system schema. It's got Fg pulling it down. That's Fg on the parachute by the Earth. All right, then we additionally have a tension force here, which is going to be pulling the parachute down. All right, Ft on the parachute by the woman. So the woman, through that tension force, is pulling the parachute down. And then the thing that's keeping the parachute up, that's F of air resistance, all right, between the parachute and the air. If we start filling in some numbers here, the parachute is 5.5 kilograms, so we know that means it's 55 newtons. Then the tension force we have from the last problem, that is 650 from with the woman, so it has to be the same. This tension force going down is the same as the tension force going up on the woman, so they need to be 650 newtons. And then for the air resistance, it needs to balance out with the two downward forces, so 650 plus 55 is equal to 705 newtons going up. All right, so for this one, we've got tension is equal to 650 newtons, and actually I'll call that Ft. And then we know that the force of air resistance experienced here is equal to 705 newtons. And those are our two answers. Okay, so that is that. Hopefully not too bad, but if you have any questions, come in and make sure that you're in good shape on all these problems. Questions on the test will be very similar to what you saw on this practice sheet.